Hi everyone, so this is our second lesson of Lockdown 2, so we're going to go through emulsions today. It links into last lesson, which was the soaps and detergents one, so if you haven't gone through that or you want to do a little bit of revision, that might be useful to have a watch of that. For today, you're going to need the following. You're going to need your Unit 2 notes, so you can fill them out as you go along or afterwards. Pen and a paper to answer some of the questions, and also your data book is going to be very useful. There's no calculations today, so no need for a calculator. So as usual, let's go through our little mini test that we do at the beginning of each lesson. So first question here. So you know the drill, pause the video, and when you're ready, come back to it. Okay, so this here is asking us about the polarity of these two different chemicals. They're quite similar, but one is more polar than the other. And here's our marking instructions here. So ammonia is polar and trichloroamine is non-polar. And the reason for this, for our second mark, is about the difference in electronegativity. So the hydrogen and the nitrogen, there is a greater difference in electronegativity compared to the nitrogen and the chlorine, and therefore that is the more polar of the chemical. Okay, moving on. Okay, so quite worded this one. Have a go at this, please. I think this is quite a tricky question, this here. So we're just looking at step number 1, and the way that I did this is I looked to try and find what was happening to each of the chemicals, and I focused really on the iodide ions, the I negative. So I looked what was happening to those. I noticed that the I minus, 2I minus, was changing into iodine molecule, and the way that that must have happened is that the electrons from the iodide ions must have been removed. So this is therefore the oxidation reaction. We can say that the iodide ions have been oxidized. So if they're being oxidized, it must mean that the other chemicals, the hypochlorite, the OCl minus ion, that must be the thing that is being reduced. So I wrote out what's happening to that. So it's changing into Cl minus, and then I balanced it, with the hydrogens and the water molecules and the electrons and so on and so on. So this here is the correct answer. So have a read of the marking instructions there, please, as well. That's important. Okay, next question. So this now links in directly to what we were doing last lesson, so this should help you a little bit with what we're going to do today. So the first part here is asking us to name the alcohol that will be formed when pentyl butanoate is hydrolyzed. So we have to find that ester link, that Q group in the middle there, and the alcohol is going to be, in this case, it's going to be towards the left-hand side. So we have 1, 2, 3, 4, 5 carbons. Therefore, it's going to be pentan 1-ol. And notice as well, because the position of the hydroxyl group is going to be on the end of the molecule, we need to refer to exactly which isomer of pentanol we have, and in this case it's pentan 1-ol, and so you have to refer to that. Next question is, draw a structural formula for the sodium salt of the carboxylic acid that will be formed. Okay, so this is going to be reacting with sodium hydroxide. So we've done the first stage of making a soap. That's the hydrolysis. We're splitting up into the alcohol, the pentan 1-ol, and then the carboxylic acid. So that would be 1, 2, 3, 4. So that would be butanoic acid. We're then going to react that with sodium hydroxide, so an acid and base reaction, so a neutralization reaction, and that's going to produce a salt. So the product would be the following. And pay attention to the marking instructions as well, please. Okay, so let's move on. So emulsion, so this is what we're going to focus on. It's not going to take too long this, but if you want to read the success criteria there, that would be very helpful. All right, emulsions. So the sort of question that we can be expected to be asked here is as follows here. So in this question here, we're being asked to say how we make something called emulsifiers, and that's quite a common question, the sort of thing that you can be expected to be asked for this here. And we've got the structure of an emulsifier given there. This next question, again, we'll go through this later on, but this is the sort of thing you can expect to see, and it's pretty much the same question. It's asking you, how do you make emulsifiers? So that's something we really need to focus on. We need to learn how to make these emulsifiers. So let's just go straight into it now. So you may have come across this term before, this term emulsions. We come across emulsions in our everyday lives all the time, really, but maybe you're not too familiar with some of them, but here are some of them. So we have them in food products, so in mayonnaise and butter and milk. When those three things there are a mixture of fat and water. We also have them in medicines. So we have, what's that there? That's cod liver oil, but many other medicines you can have emulsions. And you may also have come across paint emulsions as well. So what exactly is an emulsion? Well, this is our definition here. So we can get two types of emulsions. We can get something called a temporary, or we can also get something called a permanent, or sometimes referred to as a stable emulsion. And the degree of stability differs, I suppose, because you could think that your milk there would, if you left some milk for a pretty brief period of time, it would separate out into the water and the fat. But your mayonnaise, for example, you can keep that in your cupboard for a much longer time, so it's more permanent of an emulsion. But we can also get temporary emulsions, and I guess one you may be familiar with is if you mix oil and water together. And if you mix those together, they will stay as a mixture for a brief period of time, but very, very quickly they will start to separate out into their component layers, so the oil layer and then the water layer below. And we'll look into why that happens in a little bit. Now, to stop your emulsions from becoming temporary and to keep them as a permanent emulsion, you need to add something called an emulsifier, and that's a chemical that is added. Either it's an artificial emulsifier or it's a natural emulsifier. So for example, in eggs, the egg yolk, they have an emulsifier. So when you make mayonnaise, you would use eggs, and that emulsifier in the egg yolk would help to keep the oil and the water of the mayonnaise all mixed up properly together. If you don't have that, then you will get the separation of the oil and the water into two different layers. So we're going to look in a little structure as to how to, in a little bit, as to how to make these emulsifiers, their structures, their properties, and how these emulsifiers allow us to keep our emulsion. So the way that we make our emulsifiers is by reacting glycerol and fatty acids. So this should be a familiar reaction. We've come across this before when we were learning about esters, when we were learning about fats and oils. And if you react these together, and notice here we've only actually got one fatty acid, and that is important, we will produce our emulsifier, and then also H2O would be released. And you should notice there that we've got two sort of groups there, two sections there. We've got the OH, so the hydroxyl group. So these are going to be very, very polar sections. But we've also got that C17H35 if we're using this particular fatty acid. And that long hydrocarbon tail is going to be a non-polar region. So an emulsifier is characterized by having two parts to it, a polar section and also a non-polar section. And we'll see how in a little bit how that allows it to do its job of keeping a permanent emulsion. Before we do that though, have a little think. What sort of reaction is this here? So I'm hoping you've maybe identified that because we're getting two small molecules, joining them together to form one big molecule with the expulsion of water, that this is therefore a condensation reaction. Okay, let's move on. So the structure of our emulsifiers with our polar hydrophilic head and our non-polar hydrophobic tail is what allows it to do its job, so allows it to keep that stable emulsion. And we're going to represent them using this sort of diagram there with the skeletal structure of the covalent tail, the hydrocarbon tail, and also then the ionic polar head, hydrophilic head at the top there. So let's have a think about how emulsifiers actually keep an emulsion stable. So if you imagine, we're going to use oil and water, so if you imagine we have a glass of oil and water, and if you have the oil is going to be attracted to each other, the oil molecules will be attracted to each other via London dispersion forces, whereas the water will be attracted to each other via hydrogen bonds there. So if you stir your oil and water, the hydrogen bonds will be broken, some of the London dispersion forces will be broken, and you'll have your temporary emulsion, and they're all going to mix together. But over time, those molecules are going to separate out, and as they separate out, the London dispersion forces between the oil molecules will reform, the hydrogen bonds between the water molecules, they'll reform, and we'll get this separation to go back to this here. So we've gone for a temporary emulsion and it's gone back now into its two separate layers. But if we add an emulsifier, something slightly different happens. So here's our emulsifier. So we've added that to our chemicals, to our mixture, and we've got our non-polar hydrophobic tail there. Well, that's going to be attracted to, that's going to be able to form a London dispersion force with the oil molecule. And then another one will do so, and another one, and so on and so on and so on. All the time the ionic hydrophilic head will be on the outside, so the polar head will be on the outside. And if this keeps on happening and happening, eventually we'll get something called a micelle being formed. Now, for the purposes of demonstration, we've only got one oil molecule there. It's going to be many, many more than that, but this sort of gives you the idea of what's going to happen. And we've got a picture here of a cross-section of what a micelle looks like. So we came across those in the soaps and detergents, but it's the same, exactly the same sort of idea. On the outside we have our polar heads, the hydrophilic heads, and on the inside we have the covalent tails. Now, we're not just going to have one of those, we're also going to have lots and lots of them. So let's have a think about how this micelle, how this setup with the emulsifier allows it to keep its permanent emulsion. So what's going to happen if an oil molecule approaches that micelle? Have a think, please. So if that oil molecule approaches, well, it's going to be repelled. It can't form a bond, it can't form a London dispersion force with the other oil molecule that's trapped inside it, so it can't really do anything at all. But what about if the water molecule, what if that approaches, what will happen? So the water molecule now can form a hydrogen bond with the polar heads of the emulsifier. And so we will get water surrounding that there, and the oil won't be able to interact with the oil molecule excuse me, inside the micelle. So we'll get a situation that looks a little bit like this. And if this will be repeated again and again and again. So now we have a situation where we have an even distribution of our micelles, our oil and water is evenly distributed, and because of the action of the emulsifier, we've now got our stable emulsion. So for those of you who like little diagrams, little animations rather, this one should maybe help you out a little bit. There we go, so our covalent section is going into the oil, you mix this, the mixture up a little bit, you give it a stir, agitate it, and then your micelles will be formed. There we go. So a summary, emulsifiers have a hydrophobic tail and a hydrophilic head, so non-polar tail and a polar head. The hydrophilic head dissolves in the water and the hydrophobic tail dissolves in the oil. This forms our micelle, like so. The micelles will then prevent the mixture separating and it forms an emulsion. And we form emulsifiers by reacting glycerol with fatty acids in a condensation reaction. So let's do a few past paper questions. Okay, pause this and come back to it when you're ready. Okay, so what do we have here? So we've got our emulsifier, and in this emulsifier we've got sections which are polar, so that's the hydroxyl groups on the outside parts, but then we've also got our non-polar hydrophobic section at the top there on the right hand side. So we have to mention the fact that we have these two parts, and also then how that will allow it to work as an emulsifier. So have a read of the marking instructions here, please. And if you wrote that, that would be sufficient. I assume some of you may have gone on to talk about micelles, that would be fine, but provided you have these 2 points, that's the key parts. Next question. So this is the one we saw at the beginning. Have a go at this, please. So the way that we make an emulsifier is where we react the edible oils with glycerol, and you could either use the term glycerol or you could use its systematic name as given below. Okay, last question. So we saw this at the beginning. How do we make emulsifiers? Have a go at this, please. So we react our edible oils with glycerol. Okay. So that's us done. So we've covered, we have to state the purpose of an emulsifier. That allows an emulsion to be kept in a permanent stable state. State how they are made. We react fatty acids with glycerol in a condensation reaction, and then explain how an emulsifier creates a stable emulsion, and that relates to the hydrophobic and the hydrophilic, the polar and the non-polar parts of the emulsifier. So if you can have a go at the corresponding worksheet for this, that would be great. Get that back to me as soon as possible. And as usual, if you have any questions, please let me know as soon as possible as well. Bye for now.